We're in the home stretch now with Module 5, the final part of our Chapter 2 course. And in this module, we'll be discussing the ways in which storage solutions from IBM systems come together to make a reality the types of containerized applications and workloads that we've been discussing thus far. And for those of you unfamiliar with IBM storage solutions or storage types in general, we've taken time in this module to give you an overview of the types of storage that you may find for containerized applications and those drivers specific to things like Kubernetes. And so we'll also talk about the reasons for why CSI drivers are becoming the industry standard for supplementing storage solutions for containerized applications to give you stateful or persistent application layers. And to really drive this home and to illustrate it in a tangible way, we'll close with a demonstration of IBM storage solutions working adjacent an OpenShift container platform environment for providing stateful or persistent layers of storage for your containerized applications. Now with that, let's close out this coursework and finish up Module 5. Persistent storage for stateful applications have proven particularly challenging for the industry to master. Unlike monolithic applications, which reserve storage resources once, containers and microservices bounce in and out of existence in a characteristic that's often referred to as ephemeral. The repeating cycle of coding and testing, followed by agile production deployment, further exacerbates the storage requirement challenges for containerized applications. As a result, only those storage solutions capable of providing shared storage to both existing virtualized and bare metal application infrastructures are likely to survive. In other words, a modern storage solution must provide DevOps teams with persistent, stateful application data. It must allow for the consumption of storage on demand and the delivery of the same level of availability and performance provided by traditional application infrastructures. Another key requirement is performance. To leverage containerization for scaling out hyperscale databases on cloud hosts, persisting stream processing data, and to run artificial intelligence workloads, a fast back-end storage infrastructure is absolutely required. Legacy hard drives that read one block at a time are becoming a performance bottleneck for data-intensive applications. Designed for multiple channels and flash chips, solid-state drives are inherently parallel and are able to provide orders of magnitude higher internal bandwidth compared to hard drives. From an availability perspective, clients moving to containers are looking for industry-leading storage capabilities that include automated, policy-driven data movement, synchronous and asynchronous copy services, high availability configurations, and intelligent storage tiering. They want 6 nines, that's 99.49% data assurance and resiliency, as well as 100% data availability guarantee with multi-site options. Manageability is another big challenge for clients running containers. Clients are often looking to use tools to manage their containerized applications. These tools should provide capabilities that make it easy to deploy, manage, monitor, and scale applications. They should be part of an integrated environment that also includes private image repositories, a management console, and monitoring frameworks. Data protection is another key requirement for these clients. There are many aspects of a container environment that need robust backup and disaster recovery routines, including the state of the cluster, container image registries, and runtime information. Why is storage important for containers and the applications or services that run within them? Containers, for one reason or another, will at some point in their life cycle need to be reconstituted, that is, to be brought back into their operating state after something like a hardware failure, a crash, or a software patch or update. Although containers by design are resilient against such failure conditions, it does require administrators and users to consider how a containerized application will retain, or choose not to retain, data between these reconstituted container environments. By default, containers are inherently ephemeral environments, meaning that the data or information about their state that is created over the course of that container's lifecycle will be deleted and lost when that container's lifecycle is stopped. This includes any time a container is restarted, such as for an update or a patch, migrated to a new environment, or stopped altogether. We refer to this default container behavior as stateless. Alternatively, a stateful containerized environment is one which persists and retains data across sessions in a more permanent fashion. Using external storage devices, a containerized application can persist its data throughout and beyond the lifecycle of the container. As you can imagine, being able to store data for future long-term use has a multitude of benefits for system administrators and developers that want to leverage containers as more than a one-off environment. Before we dig more deeply into storage options for container platforms, let's take a step back and review the 3 primary storage types. For the uninitiated, it's worth taking a moment to look at which storage types are appropriate for which workloads or which environments. The first of these, and certainly one of the most ubiquitous storage types, is block storage. Typically found in databases and other systems of record, block storage is appropriate for read-write-once or RWO access modes, which is to say that in circumstances where data needs to be absolutely consistent, with no conflicting or multiple reads and writes occurring at the same time, read-write-once storage is the appropriate access pattern. However, some block storage systems have incorporated the ability to maintain that level of integrity and consistency of their data, and in such systems it is appropriate to use block storage for read-write-many or RWX access modes as well. The second class is known as file storage. These are more appropriate for read-write-once and read-write-many access modes, as the underlying file system has been designed specifically to accommodate multiple users in a multi-tenant fashion, as well as multiple threads for reading and writing simultaneously. Several common access methods include IBM General Parallel File System, or GPFS, Network File System, NFS, and Server Message Block, SMB. Popular ways to leverage file storage might include things like generalized datasets, machine learning, deep learning, artificial intelligence, logs, and more. The third type of storage, having gained significant popularity with web-based, unstructured, and eventually consistent applications and data types, is object storage. At present, there is no construct or equivalent to object storage that is natively available within Kubernetes. The most common access pattern is provided through the Amazon Web Service AWS S3 API. Objects that are typically stored include non-binary files like images, documents, snapshots, or backups, and so on. Specifically for containerized applications and services, there are two classes of storage for those that require stateful apps and long-term persistence of data. These include container-ready and container-native storage. Container-ready storage encompasses devices like SAN storage, software-defined storage, and network-attached storage. These devices support capabilities such as backup and snapshots, clones, and data replication. Another benefit to choosing amongst these options is that they allow clients to leverage existing investments that they've already made in infrastructure, including networking and storage, processes, management, and monitoring solutions. IBM Spectrum Virtualize, IBM Spectrum Scale, and IBM Cloud Object Storage are products that clients may have invested in previously, which could then be made immediately available as container-ready storage options. The alternative, naturally, are container-native storage types. These are already deployed within containers and are presented to containerized applications as ready-to-go storage, not requiring much tinkering on the part of the administrator to initialize or make available. Productized versions of container-native storage can include things like GlusterFS and OpenShift Container Storage, both of which are provided by Red Hat. They are capable of storing the object, file, and block types that I had previously mentioned in this presentation. So what benefits does container-native storage confer over container-ready storage types? Firstly, it simplifies management. A single control plane with your Kubernetes containerized environment is able to manage the integrated native storage. Secondly, both internal drives and external storage can be leveraged, giving further flexibility in terms of where application data and state are persisted. Thirdly, this architecture paradigm is consistent with the hyper-converged approach for containerized applications, in which storage and compute are able to scale independently of one another. Let's take a moment to examine these two containerized storage classes, both container-ready and container-native storage, from an architectural perspective within a Red Hat OpenShift containerized platform. As you can see from the diagram, it's possible for both container-ready and container-native storage to coexist within the same OpenShift cluster. This gives further flexibility to clients who may have a mixture of persistent options and storage devices available to them from investments made previously. Container-ready storage directly connects Kubernetes worker nodes to storage devices via a fabric and provisions volumes directly onto the storage device. By contrast, container-native storage devices consume storage either as disk drives or external storage and create a new storage pool that will then be used to create new volumes for use by application containers on the fly. What is a persistent volume, or PV? To put it simply, a PV is a unit of storage that has been either provisioned by a storage administrator or dynamically provisioned by the user in containerized environments. Persistent storage is basically a non-volatile storage like flash, solid-state drives, hard disk drives, tape, or optical media like a DVD. Persistent storage can be in the form of a block, file, or object type. Since storage in containers is fundamentally ephemeral, meaning that data is gone when the container is shut down, having persistent storage is a critical requirement for many containerized applications. A persistent volume chain, or PVC, refers to the request for persistent storage by a user. A PVC binds a persistent storage volume to the request, which usually comes from a pod or a collection of containers that might be running an application. Terms such as pod, collections of containers, or applications are often used interchangeably by Kubernetes users. In the diagram on the right-hand side of your chart, you can see that a MongoDB database is using a PVC from the gold storage class for data persistence, which is then used by a pod. In summary, this chart shows the critical part to play that storage has in successful implementation of containerized IT environments. In order to expose and leverage storage types like block storage, file storage, and so on, a Kubernetes cluster requires the use of drivers to interface with those storage devices. Currently, at the end of 2019, there are 3 types of drivers available within Kubernetes. The first of these are known as in-tree drivers. These drivers were originally bundled with Kubernetes open source distributions. However, numerous challenges manifested over time with in-tree drivers to the point that they have since fallen out of favor. For example, it was difficult for administrators to add a new volume plugin using these drivers. Instability and security issues also pose potential risks to core Kubernetes functions. As such, in-tree drivers have not been accepted since the release of Kubernetes version 1.8 and upwards. Instead, it is recommended that system admins and Kubernetes developers now leverage Flex Volume and container storage interface drivers instead. Flex Volume drivers are based on an executable model that interfaces between the drivers and Kubernetes. They are installed on every node in the volumes plugin pathway. Furthermore, if the administrator requires that the Kubernetes master nodes have attachment or detachment capabilities, then Flex Volume driver plugins will also need to be installed on the master nodes. The third and most popular option by far is a Container Storage Interface, or CSI. A next-generation interface developed collaboratively by the leading vendors of container orchestration engines like Kubernetes, CSI provides a unified and standardized approach to storage for containers. Now that we have identified 2 of the 3 Kubernetes storage types that are still in use and in favor today, Flex Volume and CSI, let's explore the basic storage operations and capabilities available for these 2 storage types. A basic and fundamental feature of any storage type is the ability to create and delete storage volumes. This operation dynamically provisions storage, such as a directory or a file system, and it also allows you to delete that volume when instructed to do so. Attaching and detaching operations are also essential. This operation will map or attach a volume to a node or a cluster when storage is required by a stateful container application. Likewise, it can unmap or detach that volume when the container is stopped. If handling file types, it can automatically mount a network file system or NFS export. Mounting and unmounting volumes makes storage available to a global path, from which containerized applications like Kubernetes is orchestrating can bind mount. This operation will bind volumes to a specified directory, creating a file system if needed, and binding the mount to a new mount point into the stateful containers directory. Unmounting will likewise unbind the mount point, releasing the bind from the file system. If handling file types, this operation will bind mount between the mount point and the stateful containers directory, or the inverse if you're doing an unbinding operation. Container Storage Interface, or CSI drivers, approach mounting and unmounting operations in a much more nuanced way than Flex Volume storage. Instead of relying upon a controller manager function to handle operations, CSI drivers use Kubernetes sidecars to handle operations themselves. A sidecar is a Kubernetes utility container within a pod which handles support tasks and jobs for the main container. At a high level, the main storage offering from Red Hat is Nuba. It is used to manage Red Hat storage services across hybrid multi-cloud environments. Red Hat GlusterFS is another popular offering, with many small and mid-sized clients utilizing it today. GlusterFS is Red Hat's Distributed Network Attached Storage, or NAS, solution. Red Hat Ceph has a strong reputation in the marketplace as a software-defined storage, or SDS, solution that can support block, file, and object types, all within a single offering. Companies that use Kubernetes on premises need data reliability and enterprise data services like encryption to meet their business requirements as they containerize and modernize their existing enterprise applications. This is a strong use case to use primary storage options like Spectrum virtualized-based systems, including IBM StoreWiz and Flash Systems 9100. Organizations using Kubernetes on premises may be experiencing today or anticipate challenges tomorrow with performance limitations that lower their productivity, particularly with workloads like AI or machine learning, and IBM Spectrum Scale is a leading solution to these scale-out performance issues. Cloud-native applications, often built using a do-it-yourself Kubernetes approach, require manageability, performance, data availability, and resiliency enhancements like backup and recovery and active archive. Such administrators and developers should seriously consider using IBM Cloud Object Storage as the foundation of their data persistence strategy. Enterprise companies that are concerned with the backup, recovery, and data persistence for containerized applications should also consider using IBM Spectrum Protect Suite, which includes Spectrum Protect and Spectrum Protect Plus as part of their architecture stack. IBM has containerized its complete software middleware portfolio. There are over 100 containerized solutions available today, making IBM one of the largest providers of container software in the industry. The software ranges from WebSphere to DB2 to API Connect to business automation, urban code, Watson AI, blockchain, and much more. IBM has taken further steps to define a faster, more secure way for clients to move their core business applications to any cloud through the use of enterprise-ready containerized software solutions that run on IBM Cloud Paks. IBM Cloud Pak for Applications accelerates the modernization and building of applications by using built-in developer tools and processes. Customers can quickly build cloud apps, while existing IBM middleware clients gain the most straightforward path to modernization. IBM Spectrum Virtualize can also serve as the main workhorse to power such workloads. IBM Cloud Pak for Data unifies and simplifies the collection and analysis of data. IBM Spectrum Scale can deliver the scale-up performance needed by artificial intelligence and big data workloads that are commonplace on the Cloud Pak for Data. IBM Cloud Pak for Integration integrates applications, data, cloud services, and APIs. It supports the speed, flexibility, security, and scale required from modern integration and digital transformation initiatives. The solution comes with a pre-integrated set of capabilities including API lifecycle, application and data integration, messaging and events, high-speed transfer, and integrated security. IBM Storage can provide the glue that unifies and integrates data persistence across multiple vendors' clouds. IBM Cloud Pak for Automation transforms business processes, decisions, and content. It consists of a pre-integrated set of essential software that enables clients to easily design, build, and run intelligent automation applications at scale. IBM Cloud Pak for Automation is ideal for applications and services that you need to automate across your ecosystem, which are relying upon IBM storage solutions to enable stateful containerized applications. IBM Cloud Pak for Multi-Cloud Management provides consistent visibility, governance, and automation across a wide range of capabilities that include infrastructure management, application management, multi-cluster management, edge management, and integration with existing tools and processes. As these environments are often involved in the orchestration of multiple containerized apps, IBM recommends container-ready and container-native IBM storage solutions. IBM Storage is container-ready today, while many vendors are still in the early stages of delivery of their container readiness, still in alpha or beta versions for their storage plugins. So what do we mean by container-ready? As your customers are moving to container-based environments, they're able to use IBM Storage as a persistent layer for both block and file architectures. IBM Storage unifies traditional and container storage and provides cloud-native agility with the reliability, availability, and security to manage enterprise containers in production. As clients scale containerized apps beyond experimental or departmental use, IBM Storage Solutions enable mission-critical infrastructure that delivers on shared storage operational efficiency, price performance leadership, and container data protection. In areas of performance, IBM uses non-volatile memory express or NVMe for our block storage portfolio. Based on internal pricing and performance comparisons with Pure Storage, IBM Storage comes in at 40% lower cost and 2.5 times higher throughput when compared to flash technologies. It also provides 50% more IOPS than other flash storage competitors. For those requiring the highest levels of availability, IBM offers multi-site replication features with their HyperSwap technology with 6 nines data assurance built into our storage arrays. Developer speed and productivity is enabled by our container tooling, which are tightly integrated into private cloud catalogs and available in public repositories. This allows for easy deployment and self-service capabilities. NetApp is a recognized vendor in the container storage space, and they've heavily promoted their messaging around a data fabric. NetApp has architectural deficiencies in the way that they've implemented their volume plugins with respect to security, and NetApp Trident does not minimize the risk when it comes to cyber attacks. NetApp also lacks the full stack solution capabilities that IBM can deliver with the flexibility of storage for block, file, and object types included under IBM Power, Z, and x86 architectures. Pure Storage is another strong competitor to our traditional block storage portfolio. They have strengthened their simple approach to sales and support, but they are immature when it comes to providing container leadership and strategy. IBM has made significant investments into a broader container strategy, while Pure Storage is only putting focus on flash array capabilities. This is a comparison summary of IBM storage for Red Hat OpenShift and 4 competitive external shared storage array vendors. For containerized security, IBM has designed intelligent volume mapping that considerably reduces the security exposure risk to data, such as if an attacker escapes a container or gains root access to the host and file systems. On the topic of multi-protocol storage, IBM is the only vendor that is able to provide multimodal storage for block, file, and object types, including support for multi-compute architectures across Power, Z, and x86. Clients are moving to the cloud-native world to simplify their IT infrastructures. Leveraging open source from an established IT vendor gives them the opportunity to use the best technologies that are based on open source collaboration and enterprise hardening. IBM storage orchestration for container plugins are open source and come with the same enterprise support that one would expect from all other IBM offerings. Finally, on the topic of release cadence, IBM keeps up to date with the open source driver releases from the community to ensure that the most current capabilities are provided to our clients. Not every vendor follows a regular and prompt release cadence, and some are lagging behind in their adoption of the latest technologies and innovations from open source. As mentioned previously, the modern storage interface approach known as Container Storage Interface, or CSI, was produced via a collaborative effort amongst leading orchestration vendors to define standards for Kubernetes and container orchestration in general. Widely known as the CNCF, or Cloud Native Computing Foundation, the joint effort to develop certified standards for containerized storage, culminating in CSI, was first recognized with the release of Kubernetes version 1.13. CSI remains to this day the recommended best practice specification for Kubernetes and container-based storage. Why is CSI so important? Firstly, it's where all current development across the industry is happening. One feature that clients frequently request are snapshots, allowing a service such as IBM Spectrum Virtualize to communicate with the CSI driver and create a snapshot copy of a volume. Instead of having to go to the virtualized user interface and creating a flash copy there, you'll be able to do so from Kubernetes itself. Furthermore, you'll be able to consume that snapshot for such things as backup or store and so on. The self-service ability to manage snapshots brings immense value to businesses and users alike. CSI was engineered and designed to remain compatible with Flex Volume plugins as well, thereby allowing CSI and Flex Volume storage plugins to coexist alongside one another in the same cluster. The Storage Special Interest Group, or SIG, continues to maintain both the CSI and Flex Volume APIs to ensure that current and future plugin releases will continue to remain backwards compatible with both storage drivers. This roadmap chart illustrates upcoming features that are to be added or have recently been added to the Container Storage Interface CSI standard. Note that these items and dates are to be considered a roadmap of anticipated releases from the open source community and are therefore likely to be adjusted or changed over time. Container Storage Interface, or CSI drivers, approach mounting and unmounting operations in a more nuanced way than Flex Storage, which handles operations from a controller manager function instead. CSI drivers use Kubernetes sidecars to handle operations, and a sidecar is a Kubernetes utility container within a pod. Typically, sidecars handle support tasks and jobs for the main container. In essence, they provide the link between the drivers and Kubernetes itself. Kubernetes CSI sidecar containers are a set of standard containers that aim to simplify the development and deployment of CSI drivers onto a Kubernetes cluster. These containers listen to and monitor the Kubernetes API, triggering appropriate operations against the CSI volume driver container and updating the Kubernetes API as needed. The containers are intended to be bundled with third-party CSI driver containers and deployed together as pods. The containerized images are developed and maintained by the Kubernetes storage community. The CSI controller consists of a CSI driver that implements the CSI controller service and one or more sidecar containers. It generally does not need direct access to the host and can perform all the operations through the Kubernetes API and external control plane services. The node component should be deployed on every node in the cluster through a daemon set. It consists of the CSI driver that implements the CSI node service and the node driver registrar sidecar container. The following chart depicts the integration between CSI drivers and the Kubernetes K8s cluster. Note that the administrators and users interact directly with the master controller node via a management path, and do not in fact interact directly with the daemon set of worker nodes. Instead, in essence, what we achieve is isolation of the data path from the control path, which ensures that the data remains accessible on the worker nodes, even if that master node should go offline, and it also reduces risk and exposure to those worker nodes from the users and administrators working under the management path. The control path is also directly interfacing with the CSI plugins available within the stateful container set. And notice again at the bottom of this illustration that the control path and the data path are both interfacing with Cloud Vendor Storage APIs, which could draw from IBM Spectrum Scale, IBM Block Storage, or IBM Cloud Storage. To close out, let's switch gears into a demonstration of how easy it is to provision IBM Block Storage within an OpenShift Container Platform version 4.2 environment. The first thing you'll want to accomplish is to install the IBM Block CSI driver. From the Operator Hub inside of Red Hat OpenShift, drill down into the storage category and search IBM items within the catalog. For our purposes, the user will provision an instance of Operator for IBM Block Storage CSI driver to leverage the operator model that OpenShift provides. There's a README provided to support the installation process, including how to set up the necessary prerequisites for fiber channel and iSCSI connectivity. There's also a step to configure a secret authentication or authorization file for communicating to the storage array. You will also need to create a storage class to make use of that storage. The next step will ask the administrator to create a subscription to the operator for the IBM Block CSI driver. By subscribing to the IBM Update channel, users are ensuring that their operator is kept up to date either manually or automatically. From within the operator, you can create instance to create your IBM Block CSI driver. This will instantiate IBM Block CSI controller and a pod of containerized services in support of that driver. A daemon set will also be created on each of the worker nodes, labeled as IBM Block CSI node for each node. If your cluster contains 5 worker nodes, then this would create a daemon set of 5 pods of CSI worker nodes. Installing databases, toolkits, and applications atop of this provisioned storage is handled simply and elegantly via OpenShift's GUI-driven interface. From the Operator Hub, once again, you can drill down to databases and select a database of your choosing, either from the community or from the Red Hat certified catalog. Subscriptions to operators apply in the same way, ensuring that operators are installed correctly and are kept up to date. From your installed database operator, in this case demonstrating with the Cockroach DB, you can click Create Instance to then define and customize your database instance. For our purposes, we want to ensure that the newly provisioned database containers make use of the IBM Block CSI storage that we just created. Integrating the storage is as simple as changing the single parameter storage class from null to your storage class instance. After the user has configured their database environment with operators, they should immediately notice that with 3 replicas specified for the database being provisioned, there are now 3 persistent volume claims, or PVCs, that have been created and are now bound to the 3 persistent volumes. Toggling over to the administrative panel for your IBM Block storage, you'll be able to find the matching entries for these PVCs under the list of volumes claimed on IBM Block storage. Your database instance and its associated IBM Block storage are now both running as containerized environments within the OpenShift Container Platform cluster. The following chart illustrates help and contacts available to you should you need them. It also contains a set of links that you can bookmark for quick access to all of IBM's storage sales assets and education available today on Seismic. Let me congratulate you on the hard work and time that you put towards these 5 modules covering the whole of the Chapter 2 story between IBM Systems, IBM Cloud Paks, and Red Hat OpenShift. The opportunity presented by a combined IBM and Red Hat portfolio will continue to expand, and as we move into 2020 and the architectures between the 2 platforms become more closely aligned, we'll see increasing value and opportunities gained for our clients. With that in mind, feel free to reach out to myself, Chris Bianco, if you have additional questions about the material covered in this course or other courses, as well as tap into the resources available to you on Seismic, which encompasses recordings like these, enablement presentations, client-facing presentations, as well as other materials that are available to both IBMers and business partners alike.